Hi everyone, this is Sunny Kumar from IIT BHU and welcome to my channel Code with Sunny. And today I am going to discuss the problem incremental queries of February circuits 2021. Okay, so let's jump directly into the problem statement without wasting our time. So in this problem we have been given an array consisting of n elements a1 up to an and we must process n queries. Okay, there are queries also given. So also there are two types of queries, that is type 1 where L and R are given and we have to replace the lth element by R, that is substitute AL equals R. And there is a query of type 2, that is L and R are also given. In this case we are required to print the minimum number of operations to make all the elements equal in this subarray, that is subarray between the indices L and R. Okay, now we can perform the following operation, that is when the query of type 2 is given, we have been given L and R, lower bound and upper bound of the subarray, and we have to we have to print the minimum number of operations to make all the elements equal in the subarrays. Okay, now what is the operation? Select any index L bit of the subarray and replace AL with either AL plus 1 or AL plus 2. Okay, so basically we have to increment the any index, that is any element at the index of the subarray by 1 or by 2, and we have to find what will be the minimum number of operations to make all the elements equal in that subarray. If the query of type 2 is given, then we have to do this. Okay, let's discuss the input format also. Also there is a note given, we do not have to modify the original array in the query of type 2. Okay, we just have to only print the minimum number of operations and go further. The input format is first n and q, number of elements in the array and number of queries, and the n space separated integers, the elements of the array, and we have been given q queries. Now it will have the type like type lr. If type is 1 we have to do this, otherwise if type 2 is 2 we have been given l and r also, and we have to print in case of type 2. Okay, print a single integer for every query of the second type. Okay, note that here constraints is very much useful, because you can see n is going to vary up to what, 5 into 10 power 5, and similarly q is going to be vary up to 5 into 10 power 5. So and also array values are up to 10 power 9. So it is obvious that O of n square, or you can say O of n into q solutions, will not pass all the test cases. So we need to think upon for an efficient solution. So let's move further. So what is given actually in this question? We have been given an array of n elements and q queries, two types of queries. Type 1, change the query of, that is change the array element at the particular index, and if type 2, print the minimum number of operations to convert, that is to convert every element of the current subarray equal, that is make every element of the subarray equal. And what is the operation? That is cost of one operation, or you can say what is the operation that we need to do. We can change any element of the current subarray to either ai plus 1, that is increment by 1, or increment by 2, and the cost of doing such will be 1. So for every query of type 2, what would be our efficient way, that is you can say, or what would be our goal to solve this problem for every query of type 1 as well as 2? Note that we have to update, that is change the array element at the particular index. And how we are going to, just we can say we are going to change al equals r, but we need to do some operations in case of query of type 2 where we have to get the minimum number of operations. So how we are going to do we are going to do this, so let's understand that also. Now perform the update operation most efficient way is our main goal, and get print the answer in query of type 2 in most efficient way. Okay, now let's move further with some examples. Suppose we have been given an array of type this. Okay, let me understand with this one. So suppose this is basically, let me take some color. Suppose this is basically any subarray. Okay, this is the subarray of the given array. Let's say this will be a subarray of the given array. Now what will be the minimum number of operations to convert, to make all the elements of this subarray equal? Note that the minimum number of operation would be what is to make all the elements equal to the maximum element of this subarray. That is, we need to make all the elements of this subarray equal to maximum element, because we cannot do the increment operation for what maximum element to make equal to the element which is just, or you can say which is in value lesser than the value of the maximum element. We cannot make that element, that is we cannot make maximum element equal to some other element, because we are always intended to make the increment operation by 1 or by 2. So we need to make all the elements equal to the maximum element. This will be our goal, to make the subarray, that is to make the, or you can say you can find the minimum number of operations to convert all the elements of this subarray, or you can say my subarray, or you can say current subarray. All the elements should be equal. So we are going to make all the elements equal to the maximum element. So we are going to find the maximum element. Let's say we are having 5 here. So how we can, what will be the minimum number of operations? Let's understand this. Let's understand that, that is, suppose we have 5 here. Now you can see all the 5 is odd. So all the elements that are odd, that is 3, and only 3 is here. So we can do that. We can always, if our maximum element is odd, we can, its parity is also odd, so all the elements whose parity is going to be odd, we can just increment it by 2, and it will cost me what? One operation, that is 3 to 5 up to 7, if 7 is the maximum, and it goes on. Okay. Now if the parity of maximum element is odd, we need to look for all the what? All the elements whose parity is going to be odd. And similarly, if maximum element has parity is going to be even, our main goal is to make all the elements even first. Why make all the elements even first? Because we all know that jumping by 2 steps, and it cost me one operation. So our main optimal way is to use one operation and jump by 2 steps rather than jumping by 1 step. That's why I'm going to make all the elements parity equal to the maximum element parity. That's then only we can jump uh, at every operation, that is, or you can say at every step jump by 2 step further, that is 2 step close, or you can say 2 step forward to the maximum element. That is, we are always trying to move to the maximum element. So this will be our main operation. And suppose here in this case you can see we have the maximum element as what? 6, whose parity is what? Even. So our main goal is to make every element even first. That is, you can see 3, and here it is 3. So our main goal is to make 3 to what? Some even number, and by in the we can use one operation, that is incremented by 1. So we can make it 4, and we can make it 4. Now we can use a direct step of what? You can say I can make direct it to 6 using by jumping 2 steps, and it cost me a single operation. Now if the parities of maximum element is what? Even, then we make all the elements even, and if parity of maximum element is odd, we make all the elements odd. Then we can easily what? Do the operation of what? Jumping of 2 steps. Okay. Now what will be the answer in the, in this case? That is, you can see here what we have. Okay, let me write here. In this case you can see, let me change my color first. In this case, what how we can get the answer, that is, what I am going to do is, let me take my maximum element, or we can denote it by m. Suppose we have maximum element as m, and I am going to multiply it by L, that is length of the current subarray. It denotes that we are going to fill all the elements by what? Maximum element, and we are going to subtract my S, that is current subarray sum, that is sum of this subarray, and we are also going to what? Subtract my what? Number of elements whose parity is opposite to my current parity. That is, if it is 5, and we are going to 5 is odd, so we are going to count the number of elements whose parity is going to be even. So I am going to write it opposite parity as P, and if we convert all these elements, that is all the opposite parity to the parity elements to the same parity, I am going to do this, and it will, number of operations to convert all the elements will be this divided by 2 plus number of operations to convert the opposite parity to the same parity. That is, our answer would be this one. Let me highlight this again. So to convert minimum number of operations to convert all the elements to make all the elements equal in a subarray would be what? M into L. M is the maximum element into L is the length of the subarray minus the current subarray sum minus P, number of elements whose parity is going to be opposite to the parity of maximum element, divided by 2. Note that why I am doing this, because first I am going to make the opposite parity elements equal to the same parity as of maximum element. Then I am going to subtract this number of elements that I have increased, that is this sum, minus I have incremented every that element, that is opposite parity element, by 1. So I am going to subtract P. Then the current complete sum, that is M into L, minus this sum divided by 2, will be our minimum number of operations to convert every same parity elements to the maximum element, plus P. P is added because to convert the opposite parity elements to the same parity as of maximum element. Okay, so this will be our minimum number of operations to make all the elements of the subarray equal. Now here stops the main logic, but here it is some more trick that I have already discussed, that is the n and q is going to be the very much large. So what one naive approach is to change the maximum element and fill it, and then we have to find the minimum number of operations. Then we are going to iterate from L to R. But suppose in the case every time L is going to be given like 1 to n, and for every 5 into 10 power 5 queries, our time would exceed much more, because it would take O of n into q time, that is 25 into 10 power 10 time. So it is obvious that our all the test cases will not pass. So how we are going to do this? In that case, we are going to build a segment tree. So let me discuss my approach, how we are going to do this. This is my naive approach. You have already said it will give you 16 points, I think. Okay, but to get 100-point score, so I'm going to use a build 3 segment trees. Why segment trees? Because we all know that in segment tree, the for update operation and to get the maximum element, or you can say to get the sum or to get the count, everything is done here in the O of log of n time. So in O of log of n time, that is there are 5 into 10 power 5 queries, and in log of n time, that is it will take time of O of q into log of n, which will pass all the test cases, because this is under the time limit. So I am going to build 3 segment trees. Segment tree for getting any subarray sum in log of n time, and segment tree for getting the number of elements having even parity. You can also go for odd parity. To get the number of elements having odd parity, we can always subtract the subarray length minus number of elements having even parity. So it is the same as to calculate even parity or to get the odd parity. Okay. So I'm going to use segment tree for getting number of elements having even parity. Also, I'm going to use the segment tree for getting maximum element in the given range. So 3 segment trees are required for efficient calculation of this problem. For every query of type 1, we all know that I'm going to update the subarray sum segment tree, that is segment tree that is going to calculate or give us the value of subarray sum from L to R, or you can say any in any range, and I am going to update that element and perform the modified, that is perform the update operation in that subarray sum segment tree. Also I am going to update the parity sum segment tree. If the element is going to be odd, then it will be updated. Note that I have an even parity segment tree. If it is odd, I need to update that segment tree. Also I am going to update the getting maximum element segment tree, that is a segment tree which is going to handle the maximum operations. I am going to update that also, because the array element is going to be changed, the segment tree must be modified. Now for every query of type 2, I am going to first get the number of even parity elements in the given range using even parity segment tree in log of n time. And similarly, get the sum of current subarray and get the maximum element of the current range, and we need we need all the elements of the given range to be equal to the maximum element. So what I am going to do is I am going to suppose, or you can say let's imagine that I am going to fill all the elements in my subarray with maximum element. So how every element can be reached to the maximum element? First, it needs to be have same parity of maximum element, because that's why we can every step we will we will increment my increment with two steps, and it will cost me one operation, and it is optimal. Why it is optimal? Because it will cost me one operation and I am going to jump for two steps forward. Okay, so I'm going to make first all the elements having same parity as maximum element, and what I'm going to get the answer is maximum element into subarray length minus current subarray sum minus number of the parity, the whole divided by 2, plus number of elements that has opposite parity as maximum element, because we need to convert, we need to give one operation to that element to convert it to the same parity as of maximum element. Now if maximum element has odd parity, make all the even elements, that is make all even elements by one operation, that is incremented by 1, and it cost me a single operation. Then increment every element by 2, which cost one operation for every element, and this is optimal. And if maximum element has even parity, and it is actually the opposite of the above, so our answer would be count, that is number of elements that has opposite parity as of maximum element, plus why I am going to add this, because I need to first make equal parity equal to the maximum element, plus segment length, that is current subarray length into maximum element. It is just like filling all the elements in that subarray with maximum element, minus subarray sum, that I am going to subtract this subarray sum, and it will give me the gaps that needs to be filled, minus count that I have already filled, divide by 2, because I am going to increment every step, that is I am going to use two steps, and it cost me a single operation. So our answer for that query would be this one. So I am going to write one thing here so that our viewers will not get confused. Count will be what number of elements, let me write elements having opposite parity as of maximum element in the in the given range. And what would be the time complexity? Time complexity would be what? O of q into log of n. Why? Because every building a segment tree and updating the values in the segment tree will cost me log of n, and I am going to process q queries. And what would be the space complexity? Let's discuss that also. Note that I have taken a maximum of space complexity 4 times of n. Building a segment tree of size n, I am going to use a linear array 1D array for storing the segment tree. So let's move on to the code. Now here I have the code. I have let me start with the main function. Okay, now I have a main function. Main function is going to start with here. I have taken n and q, and I have called an initialize function to initialize my segment trees. Let's move to initialize function. Okay, now I have an initialize function that I am going to array.assign n0, event.assign n0. Even is what? The, you can say, number of elements having even, or you can say, you can just leave it because it is not going to be used, or you can say even is the array that is going to store the store the elements having even parity. Suppose our ith element is even, then I am going to fill it with 1, otherwise I am going to fill it with 0. That's what even named array is going to do here. An array is going to store the variables, and segment sum, you can say a segment tree that is going to handle sum and going to give and update the in log of n time. It is going to be denoted with segsum, and similarly segeven and segment maximum. And I'm going to initialize everything with a size of 4 times of n for building the segment tree, and in case of maximum I'm going to initialize it minus inf. Okay, let's discuss some build segment tree. That is actually the, you can build the segment tree using this is for sum operations to get the sum in L to R, and also this is for what? For this is for building the segment tree for the initial array. Now if we want to get the segment tree sum, that is sum from L to R, then I is q low and q high is going to give the what current range. I need to find the sum in the current range, that is in the range q low to q high, and this function is doing here. That is this function gives the segment sum in O of log of n time. Okay, and you can see the implementation also in the segment tree. I am going to share that in my description section of the video. Now I have an update segment tree sum. Similarly, it is going to update. It will be given an index and a new value, and it is going to update, perform the update operation in that segment tree. That is segment tree of sums. Okay. Now here it starts with the segment tree for sum, or you can say segment tree for parity. Sorry, parity, that is parity equal to even, that is even segment tree. Again the same operations of what, building the segment tree and getting the segment tree, what, getting the number of elements in the given range, what, having parity equal to even. And here the update operation in even segment tree, you can see update segment even. Now here it will start the getting the maximum element from the segment tree, or you can say getting the maximum element in the given range of the array. How we can do this? We can do this in most efficient way using the segment tree. Now building maximum segment tree, here you can see. Now this is for getting the maximum element, and this is for updating the maximum element in the segment tree. And now here it ends. Now what I have initialized it. Now I have taken the input array in the ARR vector. Now if the parity of the current element is going to be even, I am going to increment, that is make the value 1 at that index in my even array. Okay, that is, you can see even of I plus plus. Now first I am going to build my segment tree of sum, and build my segment tree of even parity, and build my segment tree of maximum. Why even parity is needed? Because we need to know for any sub array what, which have the parity, that is number of elements having even parity. If we know the even parity, we can also get the number of elements having odd parity. It will be what, sub array length minus the given value. Okay. Now let us start the processing queries. We have type LR. If type is going to be 1, let's decrement it L, and we need to perform the update operation in all the segment trees. Why? Because it is obvious to modify my IF array, that is being modified. So we need to modify my segment trees. Okay, this will perform the modify operation. Okay, now we have an if we have a query of type 2, I need to print the answer. So let's first make it 0 based indexing. So let our current length will be r minus l plus 1, and our number of elements having even parity would be what, get segment tree even function is used, and again current maximum get segment tree maximum, which will give us the maximum element in my current subarray in log of n time. Similarly current sum, it will also give in log of n time. Current sum will denote the current subarray sum of the in the given range. Now if I have maintained a count variable, if current maximum is modulus 2, that is current maximum is of odd parity, then I am going to our count will be what, count will be our number of elements having even parity, because I need that opposite parity to get incremented by 1. So I need to store it what, I need to store the number of elements having opposite parity of as of maximum element. So I count variable is going to what, is going to do that here. Okay, and if the current maximum is even, so what would be the number of elements having odd parity? So count will be initialized with what, current length minus number of elements having even parity. Now what would be the our answer in this case, that is in the case for L2R, our answer would be what, current maximum into current length, that is we, like it I am going to fill all the elements with the maximum element, minus current sum, and minus count, that is going to be what, number of elements, that is I am going to do current maximum minus current length minus current sum minus count, that is all the elements will reach the same parity as of maximum element. So every element needs two of, or you can say every element needs a single operation to step to or you can say to move 2 steps forward to the maximum element. So our number of operations will be what, difference divided by 2. That is what I am going to do here, that is going to divide by 2. And finally I'm going to add my count also, because every opposite parity elements need to step one step forward to the maximum element, so that to make that parity exactly equal to the parity of maximum element. So I'm going to print answer finally in this case. So let me compile first and let me check out this is yes, it is going to passing all the sample test cases. So let me check it out. If this is going to be yes, it is giving 100% score. So if you have any doubts in any of these any of these logics, or you can any of these approaches, feel free to comment here, and I will ask the viewers to like this video, share this video, and do subscribe to my YouTube channel for latest updates. Thank you for watching this video.